Thank you. Hello, everyone. Well, first of all, my name is Jess Garcia, and thank you so much for being here today. Thanks also to RSA for having me this year for the third time in a row. And I'm going to be starting by introducing myself very briefly, so you know who is in front of you. I'm Jess Garcia. I'm Spanish. I've been in cybersecurity for about more than 25 years, so that makes me a little old. And most of the time, I've been working in DFIR. I started the company, One Security, like 16 years ago, and it has grown to be a global provider of DFIR. And also, I've been 20 years teaching for the SANS Institute. I'm a SANS instructor, a senior SANS instructor, and I've been teaching more than 10 courses over all these years. So a lot of fun, a lot of different things. Today, I'm going to be sharing with you some techniques and a little bit of tools, techniques, and research that we've been doing, which is little known to forensicators out there. And I think it's a pretty interesting way to move forward some types of detection which are escaping our, let's say, capabilities these days, right? So the idea is hunting stealth adversaries with graphs and AI. As the conference says, stronger together, right? We have graphs, which, as you will see later, I will show you are a great way of doing analysis, but for the most part is manual, so to speak. And then we're going to be seeing how AI, machine learning, comes to aid, to automate many of the things that are going to be interesting for us, especially when we think about threat hunting, okay? The idea is, let me start the timer here. The idea is, or the challenge is easy. It's like, the idea is clear, is we want to hunt for stealth adversaries. But what does it mean? Okay, if you go to one of these portals, like ransomware portals, take Lockbit. They have a web page out there which says, hey, if you are not happy with your company and you want to make some easy money, put your credentials here and your password there, okay? Can't get any easier. If you don't have multi-factor authentication, the threat actor is going to be inside of your network completely under the radar because he is using a legitimate credential, a legitimate account with a legitimate password. Now, if he moves around with those legitimate credentials, and he starts looking for information, just moving from one system to the other till he finds the file servers or whatever the information is interesting, he's going to be a stealth because for the most part, he's not exploiting anything. He's not doing any attack. He's not getting additional credentials, not necessarily. We had a case recently where the threat actor did exactly that. No type of malicious activity, just the non-legitimate use of a legitimate account, right? How do you detect that? Your EDR is not going to be saying anything because there is no malicious activity. It's going to be looking like normal activity. So what we are going to be trying to do is figure out a way of solving this problem, okay? This research, let's say, comes on top of some research I've been doing, or we've been doing during the last few years, which is the use of artificial intelligence to detect, in this case, malicious logons, okay? So you have a specific system, one single computer, and you can analyze how users are logging on and detect anomalous behavior. Malicious tends to be anomalous, so anomalous is good for us, right? So that was, if you go back to my son's talk like a couple of years ago, 3 years ago, I was presenting these results, and it was pretty impressive. I was pretty happy. I used the same concepts a little later for using the same neural network that I'm going to be explaining to you a little later, and it actually worked in other scenarios. For instance, we were able to detect malicious scheduled task remember the SolarWinds attack, supply chain attack a couple of years ago. In my presentation a couple of years ago in RSA, I basically showed how a machine learning algorithm, LSTM, very similar to what I will be presenting now, was able to detect that. And last year, we did something similar with CobbleStrike. So, well, Cool. We've detected, we identified a kind of neural network technology which actually works well for many of our scenarios. But what was the challenge? Well, detecting these at scale. And I will go back to that a little later. I will start by defining lateral movement. Lateral movement is not only logging on to a remote computer, it can be also a number of steps, okay? If you go to the fantastic Hunt Evil poster by SANS, you will find many references, many URLs out there. And by the way, I will give you at the end of the presentation a QR code that you can scan so you can get the presentation and additional information, okay? There are a number of types of activity: remote desktop, mapping network shares, PSXX, scheduled tasks, services, WMI, and PowerShell, which are typically related to lateral movement, okay? I'm not going to be going into the gory details, but in that fantastic poster, you will find what type of artifacts, forensic artifacts, help in the identification of that lateral movement. We're going to be focusing for this research or these techniques on event logs, okay? We're going to be focusing on different types of event logs. You see an example here of some of the event logs that are related to different type of activities that I was mentioned before. You have all the information in the poster, but we're going to be simplifying things tremendously, okay? Where I'm not going to be going to do very complicated stuff. I'm going to be saying, I'm going to be capturing the information of source host, destination host, user, and timestamp. That's it, okay? Sounds pretty simple. Why? Because I can get this from the event logs, but I can get that from a CM or any other resource. Cool. So at that point, what I'm going to be putting is everything together. One of the guys in my team, Tonio Diaz, who is actually the head of our incident response technical unit, has created a fantastic cool tool called Sabonis. Sabonis will collect, if you provide event logs, it will collect all that information, source and destination, host, username, also logon type, and some other things, very, very quickly. He's mad about Rust, which is blinding fast. And then Sabonis will allow us to create that CSV, basically, with that raw information. You can also get that from any other sources if you have Elasticsearch, CM, or whatever, okay? Let's say you already have your list of source, destination, timestamp, and username. What else? What we're going to be trying to do is, can I use that simplistic information from all the different hosts in my network to actually identify malicious activity? Let's start by at scale. Of course, the idea is I can feed thousands of hosts in there and see if the algorithm and the methodology actually discovers something interesting. So, well, if you look at this and you compare it with what you have on the right, well, obviously, lateral movement on a network looks very much like a graph, right? The nodes would be the computers, the connections could be the links between the nodes. Those links are going to be corresponding to a specific moment in time and a specific user, okay? Cool, so it looks like I will be able to map my lateral movement activity into graphs. And that's, as you're going to be seeing, very useful from different points of view. So the power of graphs. Graphs have been existing there for a long time, okay? It's nothing new. And actually, they use graphs in so many areas. Why can't it be useful for us as well, okay? So the first thing you need to know is that graphs are very simplistic. We like simple, okay? So we have a graph is basically a set of nodes. The relationship between the graphs is what we call the edges, okay? And there's going to be some features. For instance, the nodes are going to have a feature which is going to be the host name, the IP address, etc. Now, what we, in general, what we can do is use graph to represent different types of information, time series, images, or networks, as in our case. I'm not going to be going into the gory details because I'm going to be trying to simplify things, and I'm going to be focusing only in what is interesting for us, which could be these networks. So if I start to think about it, it's like, well, it shouldn't be very difficult to actually map my lateral movement activity to a graph, right? Because if I have a number, of a list of the source, destination, and the username, well, it should be pretty easy. What many people don't know is that graphs are not only graphs. There is a lot of science around graphs, okay? There are lots of algorithms which actually allow you to discover very interesting things, like you can search for specific nodes, find the longest path, the shortest path, centrality, etc. Many of you probably are familiar with Maltigo. Okay, Maltigo is a tool which is actually very much used in open source intelligence, which allows you to visualize all the hosts in bubbles and find what clusters exist and how you can actually relate that activity to what you're looking for. So in reality, graphs are very powerful. And what I like is that they are also simple, right? So that's interesting. So how can I actually use graphs? Okay, it's like, what are the ways like a forensicator? Because remember, I don't want to be a machine learning expert. I don't want to be a data science expert. I am just a cybersecurity guy who wants to be using the technology for my advantage, okay? So there are several tools out there. Maltigo is one of them. I was mentioning it. There are basically other tools like TigerGraph or Neo4j, especially Neo4j is a graph database. I'm going to be talking that in the next slide. And there are also other tools like Userline, which are specifically cybersecurity oriented. Userline was actually developed by a colleague of mine, a guy who I know for a long time, Chema Garcia, and basically does the analysis, the logon analysis, to identify lateral movement in a more simplistic way, but it was a good start. I really loved it when I see it for the first time. Okay, so let's go for the simple. Neo4j. Neo4j is a graph database. And what the hell is a graph database, right? You may think. It's like, most of you know SQL. Okay, SQL databases, which are basically columns, tables. They are related by other tables, which specify the relationship between the different entities. And that's easy. But when we're talking about graphs, we want a database which works very, very fast natively with graphs. And that's exactly Neo4j. But you not only want to be able to work with graphs like visualizing them, which is fantastic, but also you want to be able to do queries on them. It's like, hey, give me all the nodes which connect with this, or which has this relationship with this user, or all the nodes which are, or the relationships that happen in a specific time range, etc. So Neo4j has also a language, a query language. It's not SQL, so you cannot use SQL, but there is something similar, which is called Cypher, okay? What you're seeing in the screen now is an example of Cypher. It's super simple, okay, very intuitive. It's a way to actually query the database to get the information you want, or to create a new database with new data. So what we're going to be doing is we are going to be selecting, we're going to be providing CSV with all those relationships, those graphs, in a specific format that I will show you later. And we are going to try to visualize and to query the data, okay? No machine learning so fast, but it still is fantastic. It's extremely powerful, okay? And as I say, I don't know many incident responders and forensicators that actually apply this technique. I will make a little demo of that later. So based on these concepts, as I was saying, Chema Garcia a few years ago created this Userline tool. Userline reads event logs and actually is able to represent the lateral movement of the lateral movement of a specific data set and represent it for your analysis, and even include it in other tools like Neo4j or TimeSketch, which may be familiar for those of you in the DFIR field. Fantastic. So we can use that. That was a good first step. But we want to go a little farther, okay? So let's put it this way, if I'm investigating an incident, right, I'm going to be knowing some details about the incident, like a user, a specific moment in time, one or two hosts that have been compromised. Fantastic. But if I'm doing threat hunting and I have no clue if there is an adversary in my infrastructure, or there is no adversary, or they are in one part of the network or the other, this does not work because I don't know where to look, right? So that's where machine learning is going to be helping, okay? So stronger together. Now I have a technology which is fantastic for representing my reality, which is graphs and lateral movement. And I'm going to be trying to figure out what technology can automate the identification of anomalies, and anomalies are normally associated to malicious activity via machine learning. Okay, so let's go for it. Machine learning for graphs. We know many algorithms which work for machine learning. I was telling you before that I've been applying different algorithms for the last few years, and they work great. If you look at my previous presentation, they were very efficient in finding the malicious activity in the first 10, 20 anomalies on the network in the worst cases, most of the times the first few, okay? But how the hell do I apply those algorithms to graphs, which are actually something different? The idea is simple, is I need to find a way to translate the graph into something that can be actually ingested in a machine learning algorithm. In the end, machine learning algorithms are about, putting different numbers in the input of the neural network, and then letting the machine learning algorithm do its job, whatever it is, okay? Obviously, I cannot, it's difficult to put a graph for any algorithm. There are graph neural network algorithms which are defined to work with graphs, but when we were doing that research, they didn't do what we wanted them to do, okay? They work fine for some specific use cases, but not for the detection of anomalies. Okay, so we don't have any specific algorithm which is native to neural network, to graphs for doing our anomaly detection. How do we do that, right? And how we do it is precisely translating a graph to some kind of matrix, to vectors, right? That I can feed to the neural network. And how do I do that? Well, you're seeing an example over there. You divide the data into two different matrices. One is going to be the adjacency matrix, which actually defines how the nodes are connected between each other, and then the feature matrix, which defines the features associated to those nodes, right? Excellent. So what we're going to be doing is, this is a process, basically, which is called node embedding. I will extract the features from a graph to turn them into vectors so I can feed them to the neural network. I'm not going to be getting very technical. You guys we put a number of resources at the bottom of the slide so you can go deeper if you're interested in that, okay? So cool. So I have graphs. I translate the graphs into matrices or vectors, and then I have the ability to do a number of functionalities, among them anomaly detection. Cool. And how do I do anomaly detection? And probably this picture out there with the cats is my favorite of all the pictures I've shown in my life, because it describes so beautifully what an autoencoder is. What is that? The idea is very simple. This is an algorithm, a neural network architecture, basically, which is pretty cool from the point of view that it allows you to take the essence of something, okay? So imagine you want to create a neural network that identifies cats, okay? And that's a problem you're probably seeing in Google and many other machine learning systems out there. How does this work? Well, what you do is present the network with lots of cats. What you're seeing, do you see that the number of layers, the number of neurons decreases? Why is that? What we call that technically is dimensionality reduction, okay? So basically the neural network, from having a lot of, let's say, granularity, a lot of details, it will start removing all the details because you're squeezing it. You're saying, no, you are not allowed to have all this information. You need to remove information. So by doing this process, this dimensionality reduction process, what the neural network does is learn the important thing. If I need to define a cat, I need to find the essence of a cat, what would that be? And that's basically what that does, okay? So the second part of the game is like now I'm going to be presenting you a cat, and you're going to be trying to say if this is a cat or is not a cat. Okay? So as you can see, the second part of the neural network is doing the opposite, trying to reconstruct the data. Okay? So basically, the idea is really simple. You provide a cat. This neural network knows how to identify cats, right? And then when it tries to reconstruct the cat, if it's a cat, it will do a good job. If it's not a cat, it will have a lot of error, okay? So if I provide a standard cat, the error will be very small. If I provide a weird cat, the error will be bigger. And if I provide an elephant, the error will be huge because it's not a cat and the network cannot reproduce that, okay? It's as simple as that. That's what we call an autoencoder, okay? There are variations of autoencoders, as you will see, which are designed not for data, because the problem with this is that it just learns a cat. But what happens when you have a sequence of events, like not something which is a cat, but a cat passing through the neighborhood every day at 2 p.m., okay? So what happens if that cat, which every day passes through the neighborhood at 2 p.m., one day passes at 7 p.m.? Well, it's an anomaly, right? Is it still a cat? Good, but it's an anomaly because that cat is not supposed to be there. Do you see the parallelism with what we are trying to solve? Now, it's a normal user, so that's fine. But it's going through the places it shouldn't be going, right? Okay, so in reality, it's the same type of idea. These are called recurrent neural networks because they develop a memory of the things that are happening, okay? There are two types of there are several types or many types of recurrent neural networks, but the one which is very popular, and I've been using it very successful in the past, is the LSTM, which is the long short-term memory neural network, and transformers. Transformers most certainly make you think about the movies, but it has to do, it's a very cool algorithm, very smart, which has been using lately very successfully by many technologies, including ChatGPT, okay? So ChatGPT uses transformers. So we knew about LSTM, and we said, how about using transformers to try to solve our problem? And you guys will see the results there. I will not spoil the story, okay? So fantastic. So now we are going to, I'm going to be introducing now the simplification of all this. At this point, you may say, yes, this is super cool, but this looks so complicated. I'm not going to be creating a neural network. Come on, I'm just trying to catch the bad guy. How can you give it this simpler to me? And basically, this is Chrysalis. What we've done is create a framework. We started this project 3 years ago to make life easy for the forensicators, okay? The idea, we created the Data Science Forensics, DS4N6 project, which basically is a set of sub-projects which allow forensicators to use the technology without having to know too much about the technology, okay? Not only for machine learning, but in general for data science. Okay, I've been introducing that in multiple conferences, and basically, as I was saying, it's a number of sub-projects. Chrysalis probably and Daisy are the top guns in that project, which basically are Chrysalis is the framework which allows you to use this so easily, and Daisy is a virtual machine in which Chrysalis is inserted, so it's even easier. The only thing you need to do is download it and use it. So, just a very quick overview of Chrysalis. What we've done is create functions that are super simple. Look at that. There are 7 functions that the forensicator can know in order to operate this framework, okay? You don't need to know Python. You don't need to know Pandas. Just open Jupyter Lab. I'm going to be showing you this a little later. And you can use these commands, okay? There are some references in our website, even small courses that you can take in order to figure out how this works. But as I say, it's super easy. I don't want a forensicator to actually spend the time learning all that stuff, right? So we created DAISY, the Data Science and Artificial Intelligence for DFIR virtual machine. It has a great background, and also it has a lot of tools. It comes with TimeSketch and a lot of different forensic frameworks, Anaconda for data science and machine learning, etc. So it's ready for download from that URL. So let's go now to the last part, okay, which is, but does this really work? And if it does, how can I use it? What can I do with this? Okay, I'm going to be putting this example. It's not an example, it's a case study, which is actually real data. What I'm going to be showing you is real data. Obviously, what we've done is anonymize the data, the host names, the users, etc. But what you're seeing is a real incident with real data of a threat actor called Conti, which is a ransomware threat actor, very, very powerful one. We had an incident with them a couple of years ago, and basically we've used that data for this specific incident. We know what happened, so we can compare if the machine learning algorithm and the graphs we are doing actually solve what we want to solve, okay? So it's a good example. So in this case, we got data from about 120 servers, if I remember correctly. There were 10,000 users, 200,000 event logs. And just to summarize super quick this case, Conti basically went into one of our customers. They actually got domain admin on that specific customer. And they called us, the customer called us specifically when they already were domain admin. So it was really around the clock just to kick out the threat actor. The good news is that we did, okay? We played a little bit cat and mouse with them, just removing their tools, etc., while we were able to investigate. And 2 days later, he was out of the organization. So it was a fantastic case study and also gave us the data to do this demo. So I'm going to be playing a couple of videos now and explain you how this actually is going to be working. The first video, first demo, is about using Neo4j, okay? So no machine learning here. I'm going to be just figuring out if using Neo4j, using graphs, is actually provides a value to the forensicators beyond just the normal types of activity we do. Since we have collected, our source of information is going to be the raw event logs. What we're going to be doing is just generating a CSV which is compatible, let's say, with Neo4j. Okay. For that, we're going to be using a Sabonis data set, as I was describing before, but you could create that extracting the information from your CM or any other way. Okay, cool. What you're seeing now in the screen is called Jupyter Lab, okay? Jupyter Lab is a web-based environment where you can execute Python commands. And I know I just lost half of you. Oh my God, Python commands. No, I don't want to know Python. Well, the good news is that Jupyter Lab, and especially Pandas, is a very easy to learn language. And actually, for analysts, it's very, very easy. There was a very interesting study. They gave not Python, but Pandas, this library, to a set of, I think it was 8-year-old children to solve some data science stuff, and most of them were able to use it transparently. Okay, so it's not like you are going to be programming. It's more like you are going to be doing analysis. I'm not going to be going into the gory details, but this is just so you know you don't need to be afraid. Okay, really, Jupyter Lab is very easy if you have the right tools, for instance, Chrysalis or some commands. Basically, what we're going to be doing is very simplistic. We're not going to be doing anything really sophisticated in Jupyter. We're going to be loading the Sabonis data set, and we're going to be transforming so it can be ingested in Neo4j. And we can play with the graphs and all that, which is what we like, right? So I'm going to be passing this a little fast, okay? So basically, this is you load the data set, And after loading the data set, you can see that there are about 4 million event logs out there, okay? So basically, Sabonis has 4 million lines, which represent the 4 million logons in terms of lateral movement from all the different hosts. And then what you see there is that represent the output of the Sabonis data frame, okay? Easy. That part is good. And then what we're going to be doing is, if we've written a function which is build lateral movement data set, which basically translates that Sabonis format into a Neo4j format. No mystery there. So after that, we will have a data set that we can ingest in Neo4j. And the question now is, well, this is the source. As you can see here, you see the timestamp, the username, and the lateral movement. These different hosts is that the different steps that that user is taking at that moment in time. And you can see they're like 15,000, okay? So there are 15,000 lateral movements, which is not bad, right? I mean, obviously, if a user connects to just one computer, that's not recorded, but if it's more than one computer, 2, 3, or more, that's going to be recorded. And then we're going to be translating that to something more simple, which is based in columns, which is what a Neo4j likes, okay? So what you're seeing now on the screen is Neo4j. Neo4j, once again, is very similar to JupyterLab in a sense. It's a web interface. You connect to that web interface, and basically that provides you a window to the database, okay? We are going to be working there with Cypher, that language. Of course, there are manuals out there that can help in learning Cypher. And once you have loaded the data, you will see, I mean, we have a database that we're going to be loading, Neo4j, the default database, and that's going to be giving us the location where we're going to be importing the data. Fantastic. So what now? What we're going to be doing is loading the CSV we have previously prepared and loading it into Neo4j so we can paint the graphs. As you can see, it's not very complicated, right? 4 lines, specify the CSV, specify what type of data you're going to be creating, note the source host name, destination host name, the timestamp, and the username, and that's it. And you see the relationships between the link, which is the relationship between the different nodes with the characteristics of the username and the timestamp. And it has loaded 30,000 nodes with 9,000 relationships. Fantastic. Now, the next thing we want to do is, well, you have the information now. It's reflected also in the database itself, okay? So you can see it's actually a database of nodes and links. And what we're going to be doing now is simply representing that information, okay? So great. Is it very difficult? Well, not really. As you see, it's pink. You click here, and you have the whole graph. Cool. You already start seeing, can you see right there in the right, you see that there is like a cluster that we can clearly see over there. So just at first sight, there are things like, there may be something interesting over there, okay? This, as I say, is something similar like what you do with Maltego. And you can see for each arrow, there's going to be a relationship between the host and such. Perfect. So what we're going to be doing now is, okay, I'm doing incident response now, okay? And I know there's going to be, there was a compromised user number 54. So I'm going to be filtering all the network for a specific user, because obviously I could start digging into the individual graphs, but I'm going to be just going for a specific user that I know was compromised. I don't know when it was compromised, so what I'm going to be doing is the representation of that user. You see that user is typically operating in 3 different hosts. Neo4j will actually show you all the users operating within this host. That's how it works, okay? But that's no problem. And you see eventually, on the 3rd of December, ping, a new node pops up, okay? And then is host number 18, to which the user logs in back and forth. So it's pretty straightforward to see that what lateral movement was happening there, okay? So no doubt that, and then you can generalize that, identifying all the activity for the next day, and clearly this user 54 was accessing different hosts in the network. So it's clear that there was malicious activity, and not only that there was malicious activity, but there is a clear map, let's say it's scanning, not really scanning because these are logons, real logons, but it was somehow connecting to different hosts. Fantastic. Okay, so we've been able to see that graphs can really help in terms of identifying certain hosts. We have, if you take a look at all the map, you see a list of users and hosts that you can see manually. There's no automation there, okay? So I need to look at the relationships and so on and so forth. Then I can look for interesting things. You're seeing a Cypher query there where I can search for entries which have more than 15 links, right? So obviously that shouldn't happen. A host, probably a user, shouldn't be connecting to 15 different hosts. So that, as you can see, super easy to filter for those conditions, or even other conditions like time ranges and so on and so forth. From my point of view, when I use this, it's very native. It's very much how our brain works. Oh, let me take a look at this. Let me take a look at that. Let me filter by day. Let me filter by user. And let me analyze what happens. So it's really easy to use, and it's very intuitive, okay? Because human brains are normally well adjusted to graphs. And then you can generate the list of the users and hosts in a broader way. Fantastic, okay? So I hope at this point, I have convinced you that graphs are cool, okay? And that graphs help. The small hiccup here is that you need to know what to look for, because obviously there were a few hosts there, but this is thousands of hosts. It's going to be difficult to visualize, difficult to see clusters and such. But it's clear that if you know where you're looking, it's going to be of value. What's the next thing I'm going to be doing? What I'm going to be doing next is I'm going to be applying a machine learning algorithm. You now know the basics. Remember, remember the autoencoder, right? Which is going to be trying to detect cats, trying to detect anomalies. But in this case, it's not just an anomaly based on something strange, but based on the sequence, okay? This user always does this, this, and this. And the next day does the same. And all of a sudden, it does something different, okay? How different? Well, remember the reconstruction error of the autoencoder. The more different, the bigger the error, okay? So what we're going to be doing is, first, we are going to be showing it with an LSTM autoencoder, okay? And then we're going to be seeing with a transformer and see what happens, okay? So let's go for it. What happens? Now we are going to be using JupyterLab. In here, you're seeing how we import some functions. Well, that's fine. And then what we will do is load, once again, the Sabonis output, which is this list of logons, okay? We have created this CSV with Sabonis. We are going to be reading it. As I told you, I promise you that reading all this data is super easy with Chrysalis, and it is. There's a function which says read data. Cannot get any easier, guys, right? Read data, and the tool is Sabonis. And at the end, we have those 4 million entries with that number of hosts and users. Great. What next? Well, this is basically how it looks like. We will now run this build LM data set, which will create the lateral movement that I showed you earlier. Okay, same process as before. And very easy. And what we will do is, afterwards, we have created a function which is called find LM anomalies for lateral movement detection. Okay, what is that? Well, remember I told you I don't want you to need to know machine learning, vectorization, algorithms. What I want you to be able to do is, this is my data, I want to see anomalies. That's it, okay? You now understand a little bit how the process works. And what we've done is create a fine LM anomalies, fine lateral movement anomalies. And you say, you are tricking me. I don't know what that does, okay? My answer to you is go online after this talk, download the code from GitHub, and take a look at the code. What we've done is put all the ugly stuff in a function. But you know what? Back in the time when I started working with neural networks in year 99, you had to create the neural networks one by one neuron by one. Now you create a full neural network in one line of code, literally. There is a library which is called Keras. It's super easy. So if you look at the code, we will see, really? Is it that easy to do machine learning? And the answer is yes, okay? Today, doing machine learning is very easy with these new high-level languages. So what we've done is create this fine lateral movement function. As you will see, what we will provide is, as an argument, the type of model. Remember I told you that we're going to be using two models, the LSTM, long short-term memory algorithm, and the transformer. Let's go for the LSTM, see how it works, okay? So we're going to be executing first the LSTM, and let's see what type of detection it does, okay? The LSTM algorithm, what you do basically is you provide that algorithm, you provide the data to the algorithm, and what the data does is learn first. Oh, but then you need to teach it in advance. No. What you provide is the data, okay? And with that data, he will learn what is normal and what is not normal. So it's not an algorithm you need to train in advance with some clean data set. No, you provide the data and it learns from the data. And from the data, that's what we call an unsupervised algorithm. You don't need to tell him what's wrong, what's right. No, he will learn on its own, right? And after a while, he's actually doing all the activity, and we select the 50 top anomalies. What does it mean? The anomalies, the entries with the highest reconstruction errors, okay, from the autoencoder. And we start looking at what users we have found. What you can see here is that some of the users that we find are actually malicious, okay, have actually been compromised. And together with the users, you can see over here, by the way, let me show you this. You can see over here that most of the paths that you're seeing with the LSTM, can you see it's only 2 hosts, okay? So it has analyzed all the data, but it's LSTM, for whatever reason, it's actually focusing on anomalies on 2 hosts for the most part, okay? It gets, out of that top 50, some of them are in compromise, some others are not, okay? So let's say the accuracy, quotes, is 38%. I'm going to like to talk about accuracy because remember, guys, that in this second scenario, we're trying to find if there is something strange, malicious. So it's not about accuracy. It's give me a hint and tell me if there is something which actually stands out, okay? And I, as an analyst, decide if this looks good or not. But I don't know if there's an incident, there is an intrusion. I'm trying to figure out things that are anomalies. So for me, it's not important if the accuracy is 38% or 50 or 20, as long as the malicious activity appears in that top 20 or top 50. Because I will say, oh, look at that. That's malicious. Let me pull the string and investigate, okay? So if we continue, you will see that, as I said, the accuracy, the number of entries or users that were compromised were 38%. Let's do the same with the transformer, okay? The technology from ChatGPT and so many other great advances in the field in the last few years. The transformer has a mechanism called attention. I'm not going to be going there, but just for those of you who are a little experts in this, we are not using attention here. It's not providing extra value, okay? But just we run the network. The first thing that struck us is that it's super fast, okay, much faster than the LSTM, which means that it can scale much bigger. So if I have bigger networks, more hosts, it will be faster, much faster than an LSTM. And also, can you see now that it's more focused on on paths with 3 hosts over here? Okay, in the previous example, I was pointing that this was, let me see. I cannot, okay, here it is. So if you take a look at this, they're like 1, 2, and 3 hosts. And most of the output you're seeing here is of 3 hosts. So it's clear that the algorithm is working differently than the LSTM. Great, okay? So if we continue, you will see, I mean, we analyze all the different users that are in there and all the different lateral movements. We identify a few of them. And actually, the vast majority of them and the vast majority of the lateral movement steps are malicious, okay? So correspond to real malicious activity, okay? So basically, I'm gonna be skipping this a little fast. So basically the point here is that we have overall an accuracy of 96%. Out of those 50 first entries, 96% were malicious. And additionally, 4 out of the 6 users that appear there were compromised. And you know what I really liked about this is that the results are complementary. Because if you look at the LSTM, it gave us some results. If you look at the transformer, it gave us another result. I'm not picky. I'm not friends with anyone specific. I like both, right? So I can put both together, and the results are going to be complementary. To end up with, this is, I'm going to just be skipping this because these are the results. And just the representation, you can see in red what was successful compared to the original data set, okay? So it's obvious that this helps, okay, especially when you don't have any clue if there is something malicious or not going out there. Okay, so, well, just to go back and finish the presentation, I think it's clear that this can help. I think it's clear that this weapon that we can use in threat hunting and DFIR. And I think it's a very clear also how machine learning, beyond the buzzword and beyond this hidden propaganda that we're using, it actually can be used in the real world for different purposes, okay? As always, this is how you can take it to practice. And thank you very much. This is the QR code on the left will take you to that URL where you will be able to get the presentation. Thanks to my team, especially Mario Perez, who was working very hard on that, and Francisco Cortez and Bea, for all the work they did for the presentation. Thank you very much. Hope you enjoyed. See you next time. Thank you so much.